Hello, everyone. So in this video, we'll talk again about fairness criteria and about pairwise comparison, the method of pairwise comparison, and see which of these fairness criteria are satisfied. So in this case, several of these sort of can be easily reasoned to be seen to be satisfied. So in particular, let's take a look at the majority condition, the majority criterion. The majority criterion says that if you look at the first place votes and you have a majority, that candidate should win. In other words, the candidate with the majority of first place votes should win if they exist. But if you think of pairwise comparisons, you pair up that candidate with any other candidate, and you'll see that that candidate winning the majority of first place votes must win every single pairwise comparison that they can be set up with, which means that that majority candidate will be a Condorcet candidate. And because the pairwise comparisons always will give the Condorcet condition criterion being satisfied, then you know that the majority condition will be satisfied. So, long story short, the Condorcet condition is always satisfied by pairwise comparison method. This was mentioned in the video on pairwise comparison method. And from the argument I just gave, that implies that the majority criterion will also always be satisfied. What about monotonicity? Well, the monotonicity criterion says that if you take a winning candidate with your method and you have some ballots improve their position, then that candidate will still be winning. But let's say you have a winning candidate and you look at a pairwise comparison, in other words, a head-to-head matchup with that candidate and someone else. If you improve a few of the ballots, that head-to-head matchup will only go more towards the way of the winning candidate. So monotonicity will certainly be satisfied with the pairwise comparison method. You're only improving their performance in head-to-head matchups when you improve them on their preference schedule. All right, but let's take a look at this last tricky condition, this last tricky criterion, independence of irrelevant alternatives. And let's see if that method or that criterion holds with pairwise comparison method. Okay, so I've pulled an example from the book for this particular case. And this is some example that comes from an NFL draft scenario. It has 5 candidates, and I'm not going to go through the details of how we get these results, but I'll trust that you can verify this by looking at it carefully. So you could pause your video if you want, and you can check to see that indeed these results are as claimed here. So what we see here is we see 5 candidates, and this is the preference schedule given here. And we look at every single pairwise comparison, so every head-to-head matchup, and we determine the winner. The votes are given here, so the number of votes that A received versus B is 7 and 15, meaning that B is the winner. There's one case here that we haven't seen before in the video, which is we get a tie, but as was discussed in that video, if you have a tie, that means that you give a half point to each of the candidates in the tie. And so these are the results of the head-to-head matchups. And what does that mean? That means that we can check and see what the results are going to be for the totals. So A, it looks like, is receiving 1, 2, 3 points total. So A receives 3 points. B, let's check what B receives. B won 1 point here, gets a half point here, and 1 point here. So 2.5 for B. C, well, C just gets a point here and a point here. So C gets 2 points. D, it's a point here and a half point there. So D gets 1.5 points. And then finally, E looks like it only won versus C. So E will get exactly 1 point. So in this case, the full ranking is going to give us A, B, C, D, E. So that's quite pleasant. But there it is. In particular, A is winning with the method of pairwise comparison. All right, so now what does this criterion, the independence of irrelevant alternatives, say? It says, okay, we've gone through an election, we've used a method to determine a winner, and now if any of the other candidates that did not win, the irrelevant candidates, drops out, A should still win. The winner should still be the same. So let's drop one of those candidates. In particular, let's drop the candidate C. So we're going to drop candidate C. And what you can see in this schedule here is all I've done is I've just removed C from this schedule. And if you look carefully, you'll see that the schedule below is just obtained by shifting everyone up that needs to be shifted up after removing C. So it's what would happen were C to just drop out of the race. But now, as it turns out, if you count up the votes and the pairwise comparisons, all of the same head-to-head matchups have the same head-to-head results as you would expect. They don't really change. So even the numbers are going to stay the same because they're really the remaining candidates are still having the same result in head-to-head matchups. So we have that A, but however, there's a different number of candidates, and somehow that makes a difference because A won against E. And so A was able to count an extra point, but now A can't count that point because, pardon me, A won versus C. And so A was able to count the point against C, but now that C has dropped out of the race, A can no longer count that point. So when we're doing our total tally of A, we see that, okay, A now only has 2 wins. Before A had 3 because it competed against C, but now A only has 2 wins, so it has 2 points. B is still in the race, and B, when we looked at B versus C, we saw that B actually lost to C, so C dropping out kind of helped B, or it didn't hurt B. And so we can count up the total there. B gets 1.5 and another 1, so B gets 2.5. C is no longer in the race. D received exactly 1.5 points, and E, sadly, didn't get any points. So with this, the result of C dropping out, again, didn't change any head-to-head matchup. However, it changed the number, the point count, because C lost and won to various candidates. And in this case now, we see that B wins just from the effect of that change in point count. And so that is really violating the independence of irrelevant alternatives criterion. So it is not always satisfied with the pairwise comparison method. However, this method really does satisfy three of the others, which is a better outcome than um, the other methods, if we're just considering all these fairness criteria on equal ground. Okay.